Hi, to start today, I want you to answer the question, which of these data sets is more spread out? And to do this, okay, you can judge it by eye, but I also want you to work out the range and the interquartile range, so have a go. Okay, the range is going to be quite quick for both. It's just the highest minus the lowest. They're both ordered, so it's 9 minus 2, and 9 minus 2. The interquartile range, so we split the data into two, and then we find the median of the lower half and the median of the upper half. In this case, it's going to be 8 minus 3, it's going to be 5. So we've got 100% of the data within a 7, and 50% of the data is within a range of 5. Interquartile range for this one, split it into two. We get the same thing. But you can see that they're not the same set of data, and so our measures of spread in some ways are not sufficient. Actually, if I look at this one, it's more condensed around like the middle, the 4.5. This one is more spread out. So the question is, how can we find another measure of spread that will allow us to cater for situations such as this? And the answer is variance and standard deviation. They're essentially the same thing. We'll see the difference in a minute. And we're going to look at this for both continuous and discrete data. Okay, so I've talked about the limitations of the range and the interquartile range already. They're great. They're absolutely fantastic quantities. They allow you to draw box plots, but there's still situations where they will miss things. And so I guess what I'm getting at is like the median is a way of a measure of location for some data. It looks at like exactly halfway through. And it's got some advantages. And now we've got these measures of spread, which look at certain positions. But whilst the mean accounts for every piece of data and the median doesn't, we are now going to work out a measure of spread that accounts for every bit of data in the data set. Okay, and this is how we're going to do it. I'm going to talk us through this quantity called the variance and standard deviation. So let's say I've got n data values, and I'm going to label them x1 up to xn. What I can do is I can work out the mean, okay, and that's typically called x bar. And if you're familiar with summation notation by now, it's the sum of all my x values divided by how many values I have. Don't forget that this thing is shorthand for r equals 1 up to n of xr. It's just an abbreviated version of it. So we've got the mean. That's a measure of location. What do we do now? Well, what we do is we find out how much each value deviates from the mean, i.e. the difference between them. So we just take the x1 minus x bar, x2 minus x bar, and so on. Some of them are going to be less than the mean, and some of them are going to be more than the mean. So there's a bit of an issue at the moment, because if I was to add up all these deviations, actually, I'd get 0. It would exactly cancel out. I'm not going to prove that, but you can quite quickly prove it, that you'll get 0 every time, because the ones that are below the mean will balance out exactly with the ones above. So what we do is we actually square the deviations. So the negative ones become positive, and the positive ones stay positive. You might argue, why not just take the absolute value? Why not just make them all positive? But it turns out that this has a significant use doing it this way. Okay, and this is what we write down then. So these are the squares of the deviations. And then, let's add them all up, the total deviation. Add them all up, and that gives us, actually that's a slight mistake, that should not be there. So it's all each of my x values minus the mean squared, but then I add them all up. Okay, but that's going to mean that if I have more values, I'm going to get a larger deviation than if I have fewer values. So I need to take that into account. And what I do is I divide through by the number of values. So this finds the mean squared deviation. And that is another name for the variance. Okay, so I'm hoping this makes sense. This will tell us about the spread, because the more spread out things are, the more each of these squared deviations will be. And if they're really close to the mean, the lower it will be. So it is definitely a measure of spread. And it's, hopefully you can see that from the formula. And then one final thing is to standardize the answer, because we've squared, not for no reason, but we have squared them. We kind of need to square root to get back in some sense, and that's known as a standard deviation. Okay, so these are two formulae. They're essentially the same thing. One's just a square root of the other one, and both of these quantities turn out to be really useful. Okay, there we go. There's a little summary of it. So what does this tell us? It gives us a single value. Remember, we could have loads of data about, I don't know, about a planetary system or something. And the standard deviation manages to summarize it all as one single value. Now, it's not that useful by itself, actually, but it's when you start combining it or comparing it that it becomes really useful. But in general, a large standard deviation indicates the data's points are spread far from the mean, and a small one means they're clustered close to the mean. If you had all the same value, you'd get a standard deviation of 0. I should just say that therefore it suffers from some of the same issues as the mean. It will be affected by extreme values. So if you had, some data that's really close together, and then suddenly you have like 999, then you'd get a large range. Actually, maybe I need more data points for this to kind of make sense. Right, for this, you'd get a really large range. Your interquartile range would tell you that actually it's close together. I'm not actually circled the right value there. So let's put one more value in, because then I've got 7 values. So I'd cut out this one, and my interquartile range would actually be 4, but my range would be 1,000. That will tell you that actually you've got an extreme value in there. The standard deviation will also be massively affected by this 999. Okay. Right, this formula can be quite awkward to use, in fact, because if you've got lots of data, you literally have to take every single value of x, that should have the mean a bar above it, subtract the mean from it, then square it, do that for all your data values, add it all up and divide it by n. And it turns out there's a quicker way, and it's equivalent, so it's definitely worth having a look at this. All right, well, what should we do? How should we do it? Let's do it let's go for it. Right, so this is going to be the sum, and actually the quick way is to expand this bracket out. So it's going to be x minus x bar squared. Don't forget that x is actually xr. It's just I don't write that in, but it is technically there. Now, if I do that, then it's going to become, I'm going to revert back to x, it's going to become a double bracket. And therefore I can expand it out. I can figure it out. So it's going to become, I need a bracket around this because I'm summing the whole thing, x squared minus 2 x bar x plus x bar squared. That's what happens when I expand that bracket. And I still need to divide through by n. Okay. Right, let's think about this now. So, this is going to become, there's a few things that need to be said now for me to be able to simplify this. And I'm not going to go into loads of detail on it, because it's not expected you know a lot about manipulating summation notation, but I want to talk about it a little bit to show you what's going on. So first things first, if I have the sum of a plus b, and these a's, remember, actually I think I'll put it in, if it's like r equals 1 to n. Okay, now if I'm taking AR plus BR and then I'm adding them all up from 1 to n, it's actually the same as if I did this. If I split my sum into, if I added all my ARs up added all my BRs up, and then added them together. So basically, I'm saying if you've got summation notation, you can just form two sums. And it doesn't matter that I'm dividing by n as well. I can also split the fraction. So this is going to become the sum of x squared over n minus the sum of 2x bar x over n plus the sum of x bar squared over n. Okay, that's our first little, we've just sort of used a little rule here. All right, next bit. Remember, x bar, okay, I'm going to write this one out again because this one just stays as it is. Remember, I'm summing over lots of different values of x. I'm going to keep saying that. All right, here's another little fact we can use down here. If I had, I don't know, the sum of two lots of AR from R equals 1 to n, then instead of timesing each of my ARs by 2 and then adding them up, I could actually just add them all up and then times by 2 at the end. It's kind of like, it's just, this is just factorizing essentially. So for this one here, 2 and x bar are just constants, and therefore I can take them outside the sum. It's going to become 2 x bar, and then I've got the sum of x, and I'm just going to divide that by n. And there's a very good reason I'm going to do that, and I think I've talked about it all the way up. Did I talk about it? Here we go. Actually, that thing there is the mean. So I'm manipulating this. You might think it's getting more complicated, but in fact, this is just the mean. And what I can do is I've got the mean times the mean. I can just basically get rid of this and put a squared there. Right, brilliant. Finally, I've got like a third rule I need to use. I didn't talk about this before. Let me make a bit of space. I'm running out of space. Okay, let's go up here. Let's say that I'm adding a constant. This time it is a constant, and I'm adding it from r equals 1 to n. All I'm doing is adding c plus c plus c plus c n times. So it's actually going to become n times c. And that's what's going to happen here, because I'm just adding the mean squared n times. Don't forget that. I've got n bits of data. So it's going to become n times the mean squared divided by n. I can cross those off, and I'm nearly there now. So this is going to become the sum of x squared over n, and then check it out. These are now like terms. I've got minus 2 x bar squared plus x bar squared, so it's minus x bar squared. And welcome to our new formula for the variance. It's actually much more simple because we had to find x bar anyway, so we've done that. Like when we had that for the earlier formula, we had to find it. But then instead of doing x minus x bar for all the values, all I need to do is literally square all my x values, add them up, and divide by n. Fantastic. Amazing. And the standard deviation is still going to work in exactly the same way. I just square root it at the end. Note that you could write x bar as this formula here. I can't remember how it's written in the formula book, to be honest. But yeah, this is another way of writing it. And we've got our formula. And what I would say is, although they are given in the formula book, I can't remember if it's like this or like this, it is a really good idea to learn them, because if somebody says to you, why does it measure spread? It is not obvious from this last formula that it does, but if you can talk through it like I've done up here, hopefully I convinced you why that will measure spread, then you'll get a better understanding of it. Because I remember somebody after I'd left school, they're like, why on earth did we ever learn about the standard deviation? They'd kind of, because at GCSE we'd kind of learnt it, but we didn't go into as much depth as we're going to go into here. But so yeah, that first formula is really good. However, in terms of applying it, this second formula is much, much better. Now you might say, well, my calculator is going to work it out. I don't even care about this, and we'll talk about that. But if you were to do it by hand, this is how you would do it, and I presume this is how your calculator do it. So do be aware of this one as well. And there's a nice way to remember it actually, because let me type this out. It is actually the mean of the squares. Yeah, if I add up all the squares and divide by n, I get the mean of the squares minus the square of the mean. That's how, like, I used to always forget which way around it was, but learning this little not rhyme, but this little sentence has helped me out. Mean of the squares minus the square of the mean gives you the variance, and then you just square root it to get the standard deviation. Okay, I feel that's done a really good start to the lesson here. We've introduced a new measure of spread. We've shown how it's come about. We've simplified it to a new formula, and we're going to use this one. We're also going to learn how to use our calculator, but we're in a good place. All right, we've got a funky formula for the variance and the standard deviation. Let's have a go at implementing it. You're welcome to have a go at this. I've got a second example in a minute that I was going to say have a go at, but you're welcome to give it a go. Otherwise, I'm going to talk through this one. So calculate the mean and standard deviation of 2, 3, 3, 8, 8, 9. Well, I would recommend you set up a table like so. 2, 3, 3, 8, 8, 9. And we're going to use our funky new formula, so we need to work out the sum of the squares and we need to work out the mean squared. So I'd say, to be honest, a good shout would be to just quickly get the mean. Okay, and we can add these up quite quickly. 2 plus 3 plus 3 plus 8 plus 8 plus 9. Do I need to show any working for this? Well, I'd probably just write down that it's 33 over 6, and that gives me 5.5. Okay, done the mean. Then square my values, I can do that quickly. Obviously, the more awkward the data, the more awkward this process will be, like if you had decimal places, but we can do this without a calculator. Or actually, sorry, I've already done this bit. Okay, but the sum of the squares, let's figure out that bit now. 231. And therefore, the standard deviation, oh, I forgot to talk about this. The standard deviation has a symbol that looks like this. I'm not the greatest at drawing it, but actually that one's not bad. And this is actually lowercase sigma. Uppercase sigma is that. This is lowercase sigma. So you will see that for the standard deviation. I can't believe I forgot to talk about that. And this one is therefore sigma squared. They do it that way around rather than calling this one sigma and this one the square root of sigma. Okay, so then that's going to be my sum of squares, 2, 3, 1. I'm not going to write down the whole formula, look, I've got it right here. Divided by 6 minus the square of the mean, square root it all, put that in your calculator. It's actually the square root of 8.25. That's quite a nice way of writing it. And then we're going to have to round it to 3 significant figures and so on. 2.87. Done. Okay, we'll talk a bit more about that in a minute. Now, I'm going to give you an alternative way of doing it, and you're probably going to prefer it, and that is to just use your ClassWiz calculator, because it will just do all that really quickly. It kind of depends how many marks it is, how much working. So I would expect you to be able to use this method, but I would also expect you to be able to do it on your calculator. Okay, so it's in calculator mode. We need to change it to statistics mode. And then we're dealing with one variable here. Okay, it's just an x by itself. So I press 1, and then I fill in my bits of data, 2, 3, and so on. Just press equals every time. There we have it, my 6 bits of data. Now we go to option, and it's one variable calculator that I'm interested in. There we go. It actually does it all for me really quickly. 5.5 is the mean. It's done the sum of x squared, and it's worked out the variance. That's what that thing is. That's sigma squared x is telling me the variance of x, 8.25, and then it's worked out the standard deviation. That's this bit I'm hovering over, this 2.87. Now you might be thinking, what is this s squared x and sx? And that is something we don't really cover. Well, no, I don't say really. We don't cover in A-level maths, but you might have encountered it in other subjects, depending on what subjects you're doing. And it's to do with if you have a sample, I believe. I'm actually not as an expert on this, but sometimes the definition of the variance, you use an n-1 in there and in there rather than an n. So you either know what I'm talking about or you don't at this point. We're always going to use an n, we're always going to use the sigma, but there are reasons why you would use an n-1, especially when you're using a sample. So that is what this little s is. So you need to basically ignore that in A-level maths, although you might get away with it. I can't remember for mark schemes, but I would advise you use the sigma and forget the other one. But yeah, because I'm dividing by a smaller amount, I get a larger value for s and s squared. Now there is something also that I have not yet spoken about here, and actually the using your class whiz actually works out the minimum and the maximum, which is quite quick to see, but it does also work out Q1, the lower quartile, and Q3, the upper quartile. So that's really good because you know that's another way of getting the interquartile range. Although again, I would expect you to be able to get it by hand. Okay, one for you to try now. Can you calculate the mean and standard deviation of this data? Can you do it using the really efficient formula? Don't worry about the non-efficient formula, and using your class whiz calculator. Okay, let's set up our table. We've got all our x values, 2, 3, 2 lots of 4.5, 8, and 9. Okay, let's work out the sum of x first. And it's 31, so the mean this time is 5 and a sixth. I think I'll leave it exact like that, but I've done that, brilliant. Okay, then the mean squared. I feel like I should know what 4.5 squared is, but I don't. 20.25. Okay, and then the sum of x squared. $198.5. So the standard deviation is going to be the sum of x squared, 198.5, divided by 6, minus my mean squared, and I shouldn't round it, I should keep it exact. Okay, I'll figure this one out. And I get 2.527, which I probably rounded, sorry, 2.53. Let's do it on our calculator as well, just to check. So I'm going to have to return okay, sorry, my calculator's not being very responsive here. Come on. Okay, it's already in stats variable mode. Oh, I need to return to the data. Sorry, it hasn't got rid of my data from before. That's okay. Okay, that's all my data. Option, one variable calculation, and here we go. So we get the same thing as before. Yeah, I've got my 2.53, and it's worked out everything for me. Brilliant. And that's hopefully you did okay with that. Now, just before you go, right, this actually was the data from the very start of the lesson. So I said, which of these data sets is more spread out? And yes, I know you can see by eye that the first one is, but now you see how this other measure of spread shows it as well. This one, which is more, it's got two values around the mean, whereas this more spread out up here. The second one has a smaller standard deviation. So I could show, that would be another piece of evidence. And if I have lots of data, it will be even more useful. Okay, have a go at these two questions. So the first one, you do see this sometimes, not sure on the new specification how likely this is to come up, but it could do. They actually don't give you the data set at all. You don't know what the data is, but they've given you the sum of x and the sum of x squared and asked for the mean and the variance. For this, we can't use our calculator, like we did before. We're going to have to know the formula for the variance. So first of all, let's work out the mean. That's just going to be the sum of x over n, which is 290 over 10, or 29. Very quick. And then the variance, which is sigma squared, is this. I'm just going to write down the formula. It's like the more you write it down, the quicker you'll remember it. So it's going to be 8469 over 10 minus 29 squared. And we get 5.9. Brilliant. So hopefully you are happy with that. Okay, one more. What if I give you some numbers, but some bits are missing, and then I give you the mean and the variance? Can you work back to the data? Don't you just love these sorts of problems when it all gets turned on its head? This just tests whether you can substitute in and rearrange, to be honest, but it brings other aspects of maths into it, and you can easily get caught out. Alrighty, so we've got the mean is 6, because we need to remember our definitions of the means. So we know that A plus B plus the rest of this, which is 20, divided by 5 is equal to 6. I can times through by 5 to give 30. I can minus 20. A plus B must equal 10. Okay, and then I've got variance of 2. So now I need to work out, I'm going to use that formula. I'm just going to write out again. So I know that sigma squared is the sum of x squared over n, that was meant to be a squared, minus x bar squared. So I can write down that 2 is equal to the sum of x squared, that's going to be a squared plus b squared plus 8 squared plus 5 squared plus 7 squared, that's 138, divided by 5 minus 6 squared. Okay, I can manipulate this. So what I would do is do 2 plus 6 squared, then times by 5, then minus 138. I'm going to get a squared plus b squared equals 52. And we have ourselves a quadratic simultaneous equation to deal with. So let's make a bit of space. Okay, what's the best way to deal with this? I think some substitution. A is equal to 10 minus b. Going to replace this a by that. expand this bracket out. So don't forget about the cross multiplying. I'm going to get plus b squared plus another b squared, so it's going to become 2b squared, and that's going to equal 52. Rewrite it as the 2b squared first, minus the 52 from both sides, and we've got ourselves a quadratic. Divide through by 2 because there's a common factor. Factorize. B, it's got to be double negative to make it positive 24 and minus 10b. So b is 4 or 6, and then they have to add together to give 10. So a is going to be 6 or 4, but a is greater than b. So finally, a equals 6 and b equals 4. And we've used our knowledge of the variance of the mean. We've then solved a quadratic simultaneous equation to work out these values. Okay, actually, the last thing I want to talk about, just this is more bonus material, I suppose. And I just wanted to share with you this. So a guy called Chebyshev, back in the day, found out, I don't know how he did this to be honest, but found out that this is true for any data. At least 75% of it will always be within 2 standard deviations of the mean. It's not possible for it to be otherwise. 89% must, and these are like, these are lower bounds. You could have even more. And so here's some other ones. I don't actually know about 1 standard deviation of the mean. I've got root 2 lots of it. So that can actually be really useful to look at that as well. Not just look at the standard deviation by itself and say, yep, this is a measure of spread, but actually then relate it to your data yourself. And if I go to this web link, I'm only showing you a bit of the screen here, but they've got some numbers and they've worked out, they're showing the calculation of the standard deviation, and there's quite a nice little graphic about your data and where 1 standard deviation is. So in this case, not all of it's within one standard deviation. Actually, it's not possible that it could be, I don't think. But you could go onto this website and like play around with it. Maybe I should go back to our other data. So let's do 233,889. Okay, and that's worked it out, and it's got the mean here, and then it's to give me 1 standard deviation, which is quite interesting to look at, I think. It also talks on this page about the sample student standard deviation, which I've touched upon. We also looked at if I change these to 4.5. So feel free to have a little play with this. It doesn't look at 2 standard deviations, but we will be looking back at that. It's nice to touch upon this idea, I think.